Good afternoon or good morning, wherever you are, maybe good evening even. I am Marcela. As Eugene said, I'm a PhD student at Department of Computer Science at the University of Oxford. And I'm really happy to be able to do this presentation here today because this visit that Eugene just talked about on the Complexity Hub in Vienna last year was only possible because of the travel grant of the chapter. So I would like to say you all that I really appreciate that the committee trusted me on this travel grant. And then this event I attended in Vienna, it's one of, I would say, on the winter time is one of the most important ones. On the summertime there is one happening on the US that I'm trying to go this year. So yeah, thank you very much for making it possible for me and also for other students as well. The theme of the discussion today is simulation to structure, parameter estimation of agent-based models. But please don't run away. We will go through all these words with time. And at the end, I will also show a case study of using neural networks to do simulation-based inference on the parameter estimation of a labor market ABM. We will get through all those names on time. Please don't sleep. Please don't run away. It's gonna be worth it, I hope. Right. So also I'm using like a Linux machine, so the probability of getting stuck on the slide here is high. So yeah, I'm trying to. Okay, here we go. So what we're gonna be doing today is basically I will do a very general definition of ABM because there is no just one definition. It's basically the definition that we want to assume in our research. Then I will talk a little bit about the ABMs applied to economic research. ABM has been used in so many fields, mainly on the last 20 years, I would say, given computational power, data, and data knowledge and representation. ABM has been used, for instance, to model the impact of COVID on the economy, also the COVID spreading. There is a lot of ABM on traffic modeling as well. Very strong in ecological research as well. Anything that we deal that with hierarchy or randomness. And then what I have been researching so far is the application of IBMs to economic research. Then we will talk a little bit about the parameter estimation of those models and the challenges. Why is that challenge? Why is that worth it to have a PhD on this topic? And whole a bunch of conferences on this topic. Then we will talk a little bit about what is the parameter organization and what knowledge organization has to do with it. We will take a look on the pipeline that I have been studying and trying to improve. Then I will discuss the methodological approach I have been using so far and the challenges lying ahead, and a little bit of the work in progress. In case I'm a third year PhD student, so by next academic year, I'm really looking forward to close the experiment and start like the writing part. So if you have any feedback on terms of things that you don't see it being done on time or anything like that, it's very, very welcome. So the agent-based modeling definition that we will be using here is having this model where we have stochastic dynamic behavior, and where we also deal with states that evolve through interactions and heterogeneous agents governed by behavioral rules, and if possible, generating emergent aggregate dynamics. So it's these stochastic models that when the agents follow specific rules, but they are also dealing with probability, we see emergent behavior. So on the studying agent-based modeling, one of the first things that we see online or that the professors ask us to do is to study the programming part of it using a program language called NetLogo. It's a very interesting platform because the program language is basically done for is basically tailored to ABMs. There is like an interface for the users as well. You can also load models that are pre-coded there already, just to see how the how is like a IBM should run, let's say. So they have very good examples there. Still today there are a lot of conferences that teach people how to do net logo, or only like conferences only on net logo. So this is like the initial step to study agent-based modeling, and then on a more like ABMs applied to economy. I will do a little bit of advertisement here for my supervisor, Don Palmer. He's my third supervisor. I work with Don on this very like complexity-based theory. And on the last years, he launched a book called Making Sense of Chaos, where he discussed all the applications of ABMs to economy, but he also builds this very strong case that they had building an ABM to model the impact of COVID on the UK economy, and how that was really well done. Like the probabilities that they got were really similar to reality. So he also builds the case on this topic in this book. So in turn, like to save us some lines, even though I love talking, but to save us some lines, we do have some mathematical definition. Again, there is no unique definition because it really depends on the type of ABM you want to deal with. So more generally, we will have a global state of all agents. The lowercase x here is to represent the state of a specific agent. When we have the uppercase x here, it's to represent the state of all agents. And of course, all agents, they are dependent of a previous step, the parameters that govern the behavior of the system, and then a stochastic shock, or how can I say? It can be a stochastic shock, or it can also be a stochastic behavior that we voluntarily put inside of the ABM. Some ABMs, they are deterministic, but then if you have a deterministic ABM, the estimation of the parameters of this ABM is basically a solved case. The issue arises when we are dealing with probability, where here we represent by this stochastic shock. We also have these nonlinear transitions that's where we have the beauty, if you wish, of the system, which is basically if we study the individual behavior of agents, we cannot guess the emergent behavior that will result when all these agents interact with each other and interact with the environment. And then we have the observable outputs that this is how can I say, like the observable output is what we wish the world would look like, right? So we have a model of a phenomena, and then how we want to compare, how we want to represent this phenomena is basically represented here on the with the uppercase y, and this lowercase t is the time step we are. So what we are saying here is that basically the output is dependent. There is a function on the overall state of the ABM that will give us the output of the ABM. Now, why ABM for economic research? So the there, I would say that there is a philosophical line of thought there, which is basically thinking on the economy we have now as this neoclassical conception, or traditional, as we write in our papers, and then we show ABMs as an option to that. So in this neoclassical conception of economy, the agents, they are representative, right? We consider that all agents, they have very static goals. They are homogeneous among them, and they are always rational, maximizing the profit. They also have access to the whole information of the system. They are like extremely smart. we have this economy that comes top down, right? We have equations, or we have like this invisible hand that controls the economy, and the probabilities are basically like equally divided among the representative agents, right? And the what we call here the neoclassical conception of economy, it's also very mathematical based. We have the invisible hand, which is represented in mathematical equations, and that's how the economy evolves, right? This is how we try to predict the GDP, unemployment, and the new rate of salaries based on equations. When we are dealing with ABMs, we then go to a more heterogeneous representation of the agents. We can have a population of workers, a labor force, with people having completely different salaries, completely different ways of thinking, how they will actually not only maximize, but giving a purpose of why, for instance, they would change jobs, why they would want a better salary, or why they would even just move jobs even though they wouldn't get a better salary. So we have a little bit more of economic behavior inserted on those models. We, instead of trying to go through equilibrium, like trying to reach equilibrium in economy, we go to the steady state at aggregated level, which is basically, instead of trying to solve all the equations, what we try to do is we solve every time step, and then we study the aggregates of the outputs. We also have this the source of dynamism on those models is basically on the economy. We see how we see it nowadays. When there are a shock, when there is a shock, we consider it an exogenous thing, while in the ABM, shocks and changes, they are endogenous. They come from the inside of the interaction of agents. Right? On the ABMs, we do have a bottom-up approach, which instead of having these mathematical equations that will control the whole system, what actually controls the system is the agents interacting among them and with the environment. This is why we use the computers to do this modeling, and we relax a little bit in terms of what the purpose they have and the mathematical functions they should follow, and we have a more social network based off interaction instead of just spreading the probabilities among all the agents, representative agents in ABMs. What we try to understand is how the agents behave on a network that can be fixed or changed. I will have some examples. So when we are dealing with when we are dealing with parameter estimation of stochastic ABMs, we are then dealing with probabilities, right? What we want to understand is how when we have this number of agents and we have this the vector describing the outputs, how can we get a set of parameters that will better explain this probability distribution? So, in simple words, I don't know if it's needed, but the parameter estimation of ABMs is this process of estimating a set of parameters or a probability distribution of those parameters such that this I, which is like the output of our ABM, is consistent with real world data. And here there is another philosophical thing that please send a message for me if you want me to stop explaining the philosophical part of things. But the idea here is that what we have as a sample of the real world is an event with high probability. There are a lot of combination of parameters that could result on the same output, and that's where the challenge is. So here, coming back to the equation of the ABMs, we are interested. I don't think you guys can see my the mouse here, but we are interested on this theta value here. We are interested in which set of parameters I can use that will be very strong on governing the behavior of the system, but what my ABM is producing actually has something to do with reality. This is, of course, this mix both validation of the system and also design of the model. So how this ABM parameter estimation is usually done, or okay, ABM is just like a stochastic system, how people do with other models, right? There are a bunch of other models with similar characteristics. How is actually done? Well, there are three very strong fronts to do that. One is thinking on about parameter estimation as optimization problem, right? So you have your real data, you have a real data set, you have the data that's produced by the ABM, and then you try to optimize the parameters such that you compare the output of your ABM with the real data, and you try to increase the similarity, right? Or decrease the distance. So here there are very common algorithms that we will find in papers, like the simulated minimum distance and the simulated method of moments, or the maximum likelihood estimator. All those algorithms, they are based in trying to solve optimization problem. Then we go to the Bayes theorem, which is basically how can I improve those parameters when I incorporate some prior knowledge I have the distribution about the prior distribution of the parameters, right? The most used algorithm is the approximated Bayesian computation. Even nowadays, this is the algorithm we go when we have a simpler ABM to calibrate. We go to the approximate Bayesian computation, which is basically exploring the prior distribution of the parameters, and based on the distance we have, we then change the range of prior distribution we are testing, right? If we go in a direction of the prior distribution, but the output is completely far away, so we change to another region. There are many adaptations of the ABC algorithm based on how you explore the prior distribution. And then there is the surrogate modeling, which is using machine learning or a learning algorithm to emulate the model, to emulate the ABM. So imagine that we have an ABM that would take like half a day or one day to run if we are dealing with economy, and if we are dealing with a model where we represent agents. So you imagine that this can take many hours. Some models we use here, they take a whole week to do 1,000 simulations, for instance. So this kind of method is very expensive. Some ABMs are very expensive, but to try to save some time and still have proper parameters, we can do a surrogate model. We can use a simpler version of the model that would reproduce a similar behavior, and then we do the optimization problem on that surrogate model. So probably when people do like research of ABMs and machine learning, that's where we go first, which is basically having a machine learning algorithm that will try to reproduce the ABM in a cheaper way. But then you use this cheaper version to do the calibration. So what is the challenge here? Like why is that worth it to do a PhD on this topic? Well, when we are dealing with these methods we just discussed, they have very limited expressiveness, right? We have so many like the time series of the ABMs and the economics or other models or the phenomena like the economic systems, they have such important information of how those time series evolve on time, and we basically lose most of this information when we use the algorithms that we just talked about it, right? These algorithms also they have insufficient exploration of the parameter space, because if we will we constantly get stuck in a local minima, or we just don't have computational power to explore all possible values on the parameter space, right? So that's a issue. As I said, some ABMs are very demanding in terms of computational processing and also memory. And one very important thing here is that when dealing with these algorithms, the modeler, like the person actually implementing the calibration of parameter inference, is responsible to do some very important assumptions. So, for instance, if we are dealing with the approximated Bayesian computation, the result will depend of the constants that the modeler defined. It depends on the distance measure that was used, and also the summary statistics that were used to do the dimensionality reduction, right? When we are dealing with ABMs, just imagine economy, the amount of variables we generate on executing a ABM to represent economy, the dimensionality of the vectors is really big. We cannot work with vectors this big, so we need to do some dimensionality reduction, and for that we use summary statistics. And this is something that the modeler also needs to do, and we try to make it this as automatic as possible without like a modeler, a person there required to do these assumptions. And very importantly, there is a lack of standardization of how ABMs are built. As I just started a presentation here, I told you that there is not even a uniform, like a unique definition of ABMs. And it's like how we implement ABMs, there is no framework for that. But of course, there's many papers suggesting frameworks of how you could implement algorithm ABM, like try to answer this very specific set of questions. Is your ABM doing this? Is your ABM being validated? How do you set the parameters? What are the assumptions? They are like very interesting questions. I do read those papers a lot, but there is no mathematical formalization of those questions. They basically come from literature review on what people find really hard to understand about ABMs. And yeah, and mainly on this context of ABMs for economy, what we want to do is that the output of this ABM can be interpreted, and hopefully some policymaker will see it and try to understand how the policies would impact economy. So right now I'm working on using IABM to do a simulation of the carbon budget of 2040 of the UK. So this is one thing that I'm really into it, which is trying to explain how we come up, how the results of the ABM came up, and how different values of the parameters could result on very similar outputs, and consequently very similar policies, but also at the same time how very small changes on the parameter space could cause completely different outputs. So this is the hard part to explain to policymakers, but we are up for this challenge. And we also are investigating, besides like showing the plots and uncertainty, what other things we can do, so the policymakers also understand how to run the models themselves and how to interpret the outputs. So the challenge, like why is parameter estimation of such ABMs so challenged? Talking a little bit more about the challenge I have to do on the day-to-day is basically applied to economy. We have this very large parameter space, so we cannot just random explore it. although this is how this is done most of the time, Markov chain, Monte Carlo, as much as we can. But yeah, this is not the most efficient way to export a parameter space. We are dealing with randomness, mainly on the type of work I will show to you later, which is on a label market, right? We need to make sure that in some um, in some steps of the ABM, some people will apply for a job and get this job with a specific probability, right? It's not always that you will get this job. So these things, they need to be inserted on the algorithm we're going to use to do the parameter estimation. There is also the uncertainty, right? We are really depending on the how the agent behavior will impact the outcome, how the parameters impact the outcome, and very importantly, which were the initial conditions of the ABM, right? And real data integration, which is something surprisingly recent, which is trying to align what those models do with real world data. And then just imagine the crazy amount of data shapes we have. I think this is how exactly what you do on this society, which is discuss how data is represented, right? But unfortunately, our power computers, they need to have some low dimensionality representation of data so we can use it to calibrate or validate or define the initial conditions of the ABMs. Well, so what parameter estimation has to do with knowledge organization? Well, there is this the model perspective, right? How what exactly the model is doing, what leads the behavior of the whole model. There is also how the model is processing some kind of knowledge perspective, right? How can I insert assumptions in the model in a way that I don't eliminate possibilities that could also solve my system, you know? So we need to be aware that there is a very strong relation of the posterior distribution, what we get as a result, and the uncertainty about it, with the prior information and sometimes bias and sometimes only personal beliefs we have, and how this is represented in our model. There is a very strong case for representation and classification, right? We need a structured representation of data in order to have this process in a computer or in a pipeline. We do have this issue of the summary statistics on getting this huge amount of data and try to simplify it using a list of statistic measures to describe it, that most of the time is not enough. This is why on this research I am doing, we go through the path of neural networks. We create an embedding of information on a neural network, hoping that with this technology, with this algorithm, we can do a better dimensionality reduction of the data. And of course, the different representations of data will yield different knowledge structures. So there is a huge challenge there of what would be a better representation for labor market, a better representation for the credit market, for the banks, for renting, for housing market. So we are really, really depending on representation and classification. And also integration of knowledge sources, which is again combining what the ABM reproduce, what the empirical data we have, and the prior assumptions we have about the parameters. And we also deal with a huge challenge of aligning multiple levels of description. We have micro data and macro data, right? They are really far away. We can have the descriptors of things related to the employees on the example of the labor market, but we also will have data about the whole economy in a whole country, how those two things communicate with other, how we represent the micro data such that the macro data also makes sense. So the research question I have been working on the last years is basically how we can use neural simulation based inference framework to estimate parameters of those ABMs, this large scale stochastic labor market ABMs. The labor market has been my focus here. On the things I have been putting most of my time is how we can get this heterogeneous real world economic data and integrate them on parameter estimation. It's not only for ABMs, but it's usually economic modeling is really weak on the validation. I'm sorry if there are economists in the call, but yeah, we can talk about it. Maybe like do a friendship to try to solve this problem. I also work with neural network based Bayesian inference, which is applying Bayes theory using neural networks to learn the relation of prior and posterior, and how this once we have like real economic data on parameter estimation, and we set the neural network architecture to do proper Bayesian inference, how this actually help us to understand economic systems. So the pipeline is more or less this one. This is the whole thing I have implemented already, and not my code, the PhD before me. This is what I'm trying to implement. So we basically have we have two paths. First one is train our neural network, right? We say to our neural network, this is our prior distribution, and is usually uniform because we want the network to actually explore. So we say, this is our prior distribution, that's our ABM. Produce simulated data. Once we have this data set of simulated data, we have an embedding network that will do the dimensionality reduction, right? So the summary statistics here, instead of being as a set of as a list of algorithms, is actually a network. While we do the simulations, there is a network learning the statistics that could describe that data. And then the next step is do a density estimation network, yet another neural network, which this one is actually trained to understand the relation of parameters and posterior, right? And then once we do all these steps, we have what we call the learned posterior, which is basically the posterior estimation we have with the ABM alone. Now, what happens when we do the inference step? We go to the economic data source, the real economic data. We do some pre-processing there because there are so many issues there, right? On people stopping replying surveys, or just in the case of we are dealing right now, which is the UK leaving the economic zone, Europe economic zone. So some surveys we had from the UK until 2019, for instance, we don't have anymore. So now we have to mix two surveys completely different, so we can do calibration with UK data. So this is already a huge problem in my life. It's traumatic. Let's skip. So then we have this empirical data. We use the same embedding network to do the dimensionality reduction. And then again, we go to the density estimator. And then what we're going to do now is that you say, hey, density estimator, I know you have been trained with ABM, but now I have a sample of a real data set. And then when we do this posterior estimation, depending on the real economic data, then we have what we call here the estimated posterior, because we basically condition the learned posterior on real data. I know, confusing. But I hope we have time on the questions to do a better explanation of that. Well, the case study I have here is using this methodology to do the parameter estimation of a labor market ABM. It's the labor market it's a labor market ABM of the US labor market, where we have 464 occupation, occupations, approximately 150 million workers, and the parameters there were set such that the ABM could reproduce a beverage curve, which is um, labor market economic flow that the economists believe that the labor market is always doing. And what we try to do is using this neural network algorithm to calibrate the rate of new jobs, the unemployment rate, and the probability of job retention, which is the probability of you moving to another job on the same moving to another occupation, but on the same job. Yeah, you don't change careers. That's the probability of you not change careers. So what we collect every timestamp of the ABM is the number of, so every timestamp is basically like every quarter on a hypothetical year. We collect the number of employed workers, the number of unemployed workers, the demand of the labor market, the demand of working hours, and the number of new vacancies. And this is from the paper they actually implemented this ABM. So here, they start the ABM with this network architecture here. Sorry, I will say graph, so we are not confused. So they start the ABM with this graph, with this graph structure where the connection here represents what is the probability of you moving from one occupation to another, and they apply a shock here, which is the probability of computerization of a profession. We don't need to go on the details of this shock, but it's again, this is ABM for the labor market, and the paper discusses what happens when some of these occupations are taken by computers or by algorithms. So what we do when we execute the whole pipeline for the parameter estimation, we consider that the prior distribution of all parameters are uniform. Then we do 1,000 simulations to train the neural network. Then we compare, right? We compare the dimensionality reduction done by a list of predefined statistics like means, lags, average, and the statistics we know. And we also compare what happens when I actually use another network to learn the summary statistics. Then for the density estimator, we use this algorithm called sequential neural posterior estimation. As the name say, neural here is another network to do this job, and it will do an estimation of the posterior distribution. And what we do here on the drawings I will show to you is we once we have this density estimator, we do 5,000 samples there, and then we draw posterior. So this is the details of it. What I just said is just to explain why we have this sequential name there on the algorithm. Again, this is not my algorithm. This is algorithm on the people dealing with Bayesian with statistics. So it's just explaining again what I just said, but with the proper mathematical terms. So here it's a paper that I will actually be presenting next week on the World Complexity Conference in Morocco. So what we have here is the first image is the posterior when I do the dimensionality reduction with a list of predefined statistics. So the orange line is the real parameter I used on the ABM, but of course, when I did the parameter estimation, I pretend I don't know this value, so here is just for visualization. So the picture number B is when I use an embedded network to learn the summary statistics, the dimensionality reduction of the data, and then we see that's much that's much more aligned with the real data we have. And then what we did here, okay, once we compared the list of statistics with this embedded network, we saw that the embedded networks are much better. And then we applied the same method for the whole US labor market, and the result we had is on picture number C here, also very, very good alignment. There is, of course, very strong limitations here because when we try to do, as we try to get more information of the ABM, it gets extremely heavy and the results are not aligning at all. So there is a very huge dependency here in computational power. It's not scalable depending of the information you get from the ABM. And also, when we do the validation part, there is a very specific algorithm that's used to do the validation. The validation actually gives us some research directions, which is, hey, your neural networks here, they are really good from the US label, like number B and C, they are good, great. However, there are some limitations when we do the posterior. And then here we get the research directions that I am doing at the moment, which is dealing with the data dimensionality reductions. There might be something really wrong there, or there is a huge bias on the network I use for dimensionality reduction. So this is exactly the chapters I'm writing right now, how we could solve or at least improve on those issues. So my work in progress right now is how the pre-processing of the data influence the parameter estimation, how these embedded networks can represent the ABMs better. So when I run this algorithm for validation again, I will have a better ranking here. And can this neural network estimation actually be support tools in a way that there is a way that I can make it really scalable? Is there a way that, okay, if I run a ABC, approximated Bayesian computation, is so much cheaper than actually training two neural networks to do this job. Why would I do that? Well, we need to find a way to make it scalable, right? And then there are like more day-to-day research directions I'm doing is actually searching neural architectures that better represent the ABMs, how we can improve the data that's generated by the ABM itself, and how we can integrate this micro data that we have about the economy inside of the ABM, because right now most of the work that happens on validation of those models is trying to fit the macro, yeah, not this micro. Yeah, and this is it for me.